My name is Denali Pinto, and I will be explaining Ben Fuchs's calculation problem and how I went about solving this problem. This was problem 3-31 in the book. The problem statement describes a windshield, and the objective of the problem is to determine the value of the convection heat transfer coefficient for the warm air blowing over the inner surface of the windshield to make the ice on the windshield start melting. The thickness of the windshield, the thermal conductivity of the glass, the outside temperature, and the outside convective heat transfer coefficient, as well as the temperature inside the car, are all given. For this problem, we assume steady state, no heat generation, constant K and H, and negligible radiation, as well as one-dimensional. We also assume that the outer windshield temperature should equal 0 degrees Celsius for the ice to start melting. After drawing out the resistance diagram, we can use Fourier's law and the convective heat transfer equations to find the temperature on the inside of the windshield, T2, as shown here. Using T2, we can solve for HI, which is the convective heat transfer coefficient inside the car, and I get an answer of 112 watts per meter squared times Kelvin. Now I'm going to show Ben Fuchs's solution to this problem for comparison. We agreed on the solution to the problem and solved it in a similar way. The only difference between our two solutions is that I divided the heat transfer rate by the area at the beginning of the problem, where Ben saw that the areas would cancel out when equating the conductive and convective heat transfer equations. We both ended up with about 112 watts per meter squared times Kelvin for the heat transfer coefficient on the inside of the windshield.